Okay, yeah, thanks, Hermes, for the introduction, of course, the invitation to come and present to you all today. So again, my name's Joe Davidson. I'm an associate professor of robotics and mechanical engineering at OSU and the main campus in Corvallis. And the title of our project is Robotic Smart Manipulation. And just a little bit of background. So I've been at OSU since 2018, and the name of my research group is the Intelligent Machines and Materials Lab. And so the things that I'm interested in are how do we get robots to manipulate things that are deformable, compliant, things that can bend or flexible. Those things are really hard to get robots to manipulate. And typically what that looks like is we work on making and designing end effectors, tactile sensors, and also designing controllers. And more that's using leveraging data science and techniques from machine learning and AI to train those controllers. And so the classes I teach at OSU, I teach the undergraduate courses on systems dynamics and control, and some graduate courses on systems dynamics and control. And so just a little bit of background at OSU. So we have a robotics and AI program. They're both large and growing programs. They're graduate programs, so you can go to OSU and get a master's or a PhD in robotics or AI. We have a lot of active research faculty. The university just released this new strategic plan called Prosperity Widely Shared, and it's making a targeted investment in 4 signature areas. And one of those signature areas is robotics. An example of that investment is they're building the new Wong Collaborative Innovation Complex. So this is funded partially by a gift from Jensen and Lori Wong from NVIDIA, who are OSU alumni. It's a $200 million facility that will come online next year, and it's going to have an advanced state-of-the-art clean room. It's also going to have one of the largest supercomputers in the country. And they're in the process of hiring their new director, and one of his mandates is how can we use this facility and this resource to collaborate with industry. So I think there's a really interesting opportunity going forward for OSU to collaborate with industry, manufacturing, and other applications. And so I mentioned mostly I have worked in the past in field robotics, applications from agriculture and food production and food manufacturing. And so I was really happy to have this opportunity to work with OMIC to start to work more and more in manufacturing, and that's kind of where the new direction that we're headed within my research group. Okay, so I was very fortunate to work with a great team, and so I was joined by co-PI Professor Naomi Fitter, also an associate professor. You'll hear from her a little bit later. She's in the back of the room after the break. And then we had 2 PhD students in robotics, Marcus and Trinity, that worked on this project. And our collaborators, we got a lot of great input from Boeing. Leon and Melissa Johnson really helped us scope the applications that we kind of designed this project around. Okay, so what was this project all about? What we wanted to do was automate tasks that required dexterous manipulation of things that were deformable. Cables, hoses, wires, fabric. And of course, dexterous manipulation is one of kind of the grand challenges in robotics, but typically dexterous manipulation has been confined to R&D facilities like university research labs with not a whole lot of application or transition to use in industry. Okay? And we think that robotic grasping should be intelligent and adaptive. And what I mean by that is trying to minimize the amount of constraints or fixtures that maybe we have to make in the environment. Trying to minimize the amount of controls that we have to add to the environment. And how can we do these types of tasks with grippers? They're single-use grippers for multi-purpose tasks. And then we really wanted to do that using sensing within the gripper itself, because we think in a lot of ways vision sensors are ill-equipped for these types of applications with these deformable objects. Okay, so our approach focused on using in-hand tactile sensing as the primary sensing modality. And we purchased an off-the-shelf sensor from a company in Sydney, Australia called Contactile. And this is what their sensor looks like. So it's about a 1 inch by 1 inch square. And we have these 9 pink pillars on each one. And each pillar, we have a couple of LEDs that shine light up towards a reflector at the top of the sensor. And that reflector, as it gets moved around by something pushing on those pillars, it changes the light pattern on these photodiodes down below. And the company has its own internal model that says, based on these patterns on this photodiode, I think this is getting applied this way with certain shear force or normal force or whatever, right? So that's provided by the sensor software. Okay? And then our other technique is we wanted to leverage data-driven techniques to train robot controllers to manipulate these deformable things. And where we got a lot of help from Boeing was linking our experimental studies to industry-relevant use cases, and we focused on 2 use cases. The first was how do we estimate the pose of a cable inside the gripper, and how can we use that pose, how the cable is positioned with respect to the end effector, to trace cables with the robot. And the other one was doing a connector verification check. Can we use this tactile sensing to verify whether or not we have a proper connection? And we were looking at electrical connectors specifically. So we were able to leverage some of our earlier work, and we designed a gripper for this project. It's not particularly interesting or novel, but we designed it because we needed a platform that would integrate well with these sensors. And so this was a parallel jaw gripper. It has these two fingers that are driven by a rack and pinion system. We have a torque control actuator, and we use some robot operating system as the middleware to control this thing. The first challenge that we had to overcome is, so we want to use machine learning and techniques from AI. That requires lots and lots of data. We're going to use supervised learning. That means we need ground truth labels associated with our data. And so we needed to come up with a couple of different test beds to generate this data set. And the first test bed we created was using this camera setup. And if you're familiar with supervised learning, a lot of times maybe you want to train some AI model to make sense of images. And that requires someone to look at an image and trace pixels in an image. That process is really slow, no one likes it, and that's gratitude-tated, right? And so what we wanted to do was find a way to automate this labeling process. And so this is the test bed that we did. And so you can see this set up here. We have this camera pointed down. We have our gripper with the cable, and we can use these different jigs to change how the curvature and position of the cables with respect to the sensors. And then what we do is we use color segmentation because we have a red cable against a green background. Very simple technique to identify this is the radius of curvature of the cable, and this is the entry and exit points for where that cable leaves the sensor and the gripper. And the other test bed was for this electrical connection check. And so pretty straightforward jig. We have magnets with different magnetic strengths, and then we have some copper tape that creates an electrical connection across that interface, across these two strips of the magnetic plate. And we use those magnetic plates to represent different connection points. And this is a proxy to represent different connection points at different tensile strengths for that desired connection. And we have an actuator down below that can move the gripper back and forth. Okay, so this is our test bed for generating the data set to train electrical connection check. Okay, and the other challenge that we came up with is we're using an off-the-shelf product. It has a certain form factor, and that form factor includes some air gaps in between the individual pillars. But if you want to manipulate really small wires, the problem is those wires sometimes can seat in between those different pillars based on their diameter. And so we needed a way to modify this to be able to manipulate really thin gauge wires. And the way we did that is we overmolded what we call gloves, rubber gloves, over the top of the silicone pillars. So anywhere on this silicone surface where you may get some kind of loading, that gets transferred to the sensors underneath. So the first major outcome we had for the project was training a neural network to estimate the pose of the cable. And so this is what we're trying to learn with our machine learning. We're trying to learn what's the radius of curvature, so we don't make any kind of assumption that the cable is straight or linear in between the sensing paths. So we assume that it's bent or it has some kind of curvature, so we want to estimate what is that curvature. And then we want to estimate where it enters and exits. And from that, we can try and extrapolate in space, where is the rest of the cable going in 3D space that's not actually being gripped by the gripper, by the robot. Okay, so that's what we want to learn. So we use a specific type of network called a long short-term memory network. And what it does is it takes sequence data, time series data of these tactile sensors, and tries to learn those three things that I just pointed out. Okay, so we take 50-second sequences of time steps, we pass it through our model, and then it tries to predict, and go back, again, it tries to predict entry point, exit point, and radius. And then we extrapolate that curve out. And from that, we try and predict, if we had a robot that wanted to trace some type of deformable cable, how would it move in space? So grab, predict, extrapolate, grab, predict, extrapolate. Okay. And the way that we train this is we come up with an error term or a loss function that tries to minimize the distance between where our ground truth tells us that the cable enters and exits the sensor and where our prediction is. Okay? And this is, the robot's learning this curve shows us that, A, we are actually able to learn what we're trying to. And then what the performance was is we had a mean distance error of 2.8 millimeters. So total error between the left point and the right point summed up to 2.8. But really, if you're going in one direction, you could say, let's assume that error is half of that. Okay. And then we integrated this gripper and these sensors with the UR5E industrial robot from Universal Robots. It's a platform that we have in my lab already. And integrated that. Let's see if I can get this video to play. Okay. So it's making this use the predictions right here. This green line is the predictions. Right? It's not using any camera, any vision. It's just purely making these predictions and that extrapolation and following that path based on the sensing that it has within the river. Okay. And so this example up top was one where there was a poor prediction from the trained model. And this example down below is one where there's a good prediction. Please.
So when the robot travels along the curvature,
Yeah.
is it a pre-programmed path for the
No,
robot? Or is
no. Everything's on the fly. It's deciding on the fly, right? So what's happening under the hood is at every time step where it's making the graphs, it's predicting the cable is shaped this way. It's entering and exiting here. We think the cable is positioned down in space. We need to go to this next point in space and grab it there. There's nothing to do programmed. Okay? And so just a couple of additional demonstrations of different cable poses. Okay. And just notice that right now everything's discrete, right? It grabs, predicts, moves, grabs, predicts, moves. It's not sliding continuously. And then I mentioned already that training proceeds in a single direction, so we're off about 1 millimeter in our current model. And we trained this network with 800 graphs, and it sounds like a lot, but that's really not a lot for machine learning, right? So if we were to actually go and increase the size of our data set with our test beds, we could probably get model performance quite a bit better. It just takes a lot of time and effort to do that. Okay. And so the other milestone that we had on this project was doing this electrical connection test. And we don't even use machine learning for this one. All we do is we have this actuator, we grab the cable with the gripper, and we move this actuator back and forth, and these sensors provide an estimate of the shear force across the surface of the silicone rubber. And what we do is we take that shear force, and as we start to pull, what we can tell is whether or not the cable is actually slipping. And the way that you detect that is you see a little bit of relaxation in that shear force as you're pulling, that's saying, hey, this cable is slipping. And so we use that as feedback to actually squeeze harder. And then eventually we come up and we say, have we reached a certain threshold for what our desired tensile force is for this electrical connection? And if we have, that's a successful test, it's passed. But if you separate, which we can tell with the shear force, like if you pop the connection at a threshold that's lower than your goal tensile force for that electrical connection, you say that was a failed test, right? So very straightforward way to see if you had a pass or fail in this test. Okay. And this is what the data, some of the data looks like for an example of one of the tests. Here we load the sensor, so we squeeze it, we grasp our cable. We detect a little bit of slipping because we see some relaxation in that shear force, so we squeeze harder. And then eventually we reach this threshold where our shear force says, hey, we wanted 4 newtons for this particular test. We've hit that threshold, this is passed. We haven't separated yet. Okay. And 10 different tests on, we can use that magnetic array, those 3 different values. We can say low, medium, high for a particular goal tensile force for an electrical connector. And actually, it worked better than I expected. So far, just using this simple first principles method, we're able to get pretty close to 100% success rate on fail or pass. Okay. And again, simple demo with the UR5 where you take a USB cable, you can exceed it, or you can make it a little bit offset, and you can use this technique to say, hey, do we have a good connection on the USB cable and the receptacle? So that was a pass test. The classifier said it passed. This is one where it fails. And the classifier said, hey, this won't fail. Okay. And results of the test here. Blue signal, we didn't hit our threshold. It separated before we hit that shear tensile force threshold. That failed. And hey, we hit our first video, we hit our goal force. This one passed. Okay. And so where could this work be useful in any other application manufacturing? Well, I think it could be useful where a robot needs to trace a deformable linear object, especially where you have some setup where visual perception and cameras might be degraded. So that could be continuous cable tracing, cable routing. Maybe you need to be able to trace a cable, or maybe you need to be able to route a cable around fixtures or constraints. It can also be used in applications where maybe you need to do some kind of in situ quantitative force evaluation. And so we've thought about, well, maybe if you have workers that are performing some type of test, and right now it's very subjective because we're relying on human expertise. You would actually be able to, like, to have quantifiable data that says this connector is seated. You could actually wear these sensors as a worker rather than having to put it on a robot. Okay, so we published this work at ASME had its annual conference in Portland last November, so we published that. And this project actually, it ended last summer, but we have continued to work on this area of tactile sensing, parallel work that's been funded by the Navy. And there's some limitations and constraints when you're using these off-the-shelf sensors that are rigid. And so what we've really been spending a lot of time on is how do you make flexible tactile sensors that you can shape and contour around any type of surface or any type of gripper. And this is what it looks like, our current design. So this is a flexible PCB. And I don't have it shown on here, but we take this flexible PCB, and we throw the barometric pressure sensors on each one, and then we encase those barometric pressure sensors in silicone. And now as you press on the silicone, as you press on the rubber, that's picked up as an increase in pressure that the barometric pressure sensor measures. Okay. And so this is what it would look like. Again, they're flexible, so you can contour it around a curved surface. And what we're doing now, these are videos from last week, is we have a materials testing machine. We're artificially causing objects to slip across these sensing surfaces, and we're training classifiers that say, hey, we think this object is slipping. You have some kind of slip happening. How could you compensate that through control? Okay, and that I actually finished a little bit early, but yeah, thank you very much, and happy to take any questions.